Hello, everyone. Thanks for joining us online today. So it's 1 o'clock on my clock here. My name is Samantha Lau. I'm the Manager of Communications and Operations at the Canadian Water Resources Association. Joining myself today is Meg Olson, our Executive Director, as well as Emmanuel Sims from Environment and Climate Change Canada. As you all know, we also have a great speaker lineup, James Craig and Brian Tolson from the University of Waterloo, and Jonathan Jalbert from Polytechnique Montreal. And they're all joining us for our last webinar today as part of our series we're hosting with National Hydrological Service on the research conducted through the Flood Hazard Identification and Mapping Program. Next slide. A couple of quick housekeeping notes before I move further. Regarding language and interpretation, we have our presentations in English with interpretation in French. Please make sure you're selecting the language that you would like to tune into today's webinar using the interpretation button at the bottom of your screen. To view the slides in your preferred language, you can toggle between the shared screens at the top left of your Zoom window. All slides are available in both English and French. Through our Zoom interface, you also have the option to enable closed captioning, and these are available on the bottom panel as well. Next slide. CWRA is a national organization dedicated to advancing the sustainable management of water resources across Canada. We host a variety of events, including webinars like this one today, workshops, and our annual national conference, which will be held in beautiful Penticton, BC, later this year in May. Registration is now open. This webinar is part of our 2025 series. Next slide, please. In collaboration with Environment and Climate Change Canada's National Hydrological Service. As part of this exciting series, we're highlighting groundbreaking hydrology and hydraulics research conducted through FIMP and showcasing the latest advances in flood mapping science across Canada. So I'm seeing some new and familiar names joining us today. If you would like, and I highly encourage it, please say hi in the chat and share with everyone where you're calling in from. As a national organization, we acknowledge that the speakers, as well as our audience joining us here today, are all calling in from different locations on Native lands. I myself would like to acknowledge that the land on which I work and play on is the traditional territory of the Haudenosaunee and Anishinaabe nations. This territory was the subject of the Dish with One Spoon Wampum Belt Covenant, which was an agreement between the Iroquois Confederacy, the Ojibwe, and allied nations to peacefully share and care for the resources around our Great Lakes. CWRA has created an Indigenous Relations Committee to support the organization to work towards reconciliation and allyship with Indigenous peoples in sustainable and effective water management in Canada. This is important to us, and we are committing funding, staff, and volunteer time to this work. On behalf of our team, we're welcoming any and all feedback and advice on this journey. So it looks like a few more people have joined us. Welcome to our webinar. We are recording today's webinar, and this will be freely available on the CWRA website over the next couple of weeks. In between our presentations, we'll take a few burning questions, and then again after our panel discussion. So at any time, if you have any questions, please type them into the Q&A tab on your control panel. And because we have 3 speakers, please make sure you address the speaker that you would like the question directed to. Okay, one last thing, if you run into any issues on the Zoom platform, please message us in the chat and we'll try to help you resolve them. If you do find yourself disconnected from the webinar at any point, please rejoin us using the same link once you've restored connection. Next slide. Now a quick introduction for our first speaker. Dr. James Craig is a professor of civil and environmental engineering at the University of Waterloo and holds the Canada Research Chair in Hydraulic Modeling and Analysis. He is the lead author of the Raven Hydrological Modeling Framework, a software tool used for watershed simulation and operational forecasting across Canada. His research focuses on the development and the application of improved modeling algorithms, strategies, methods, and data sets. Thank you so much, James, for joining us today. And I'm going to pass it over to you for our first presentation.
All right, thank you very much. Let me get to sharing here. And all right. So thank you very much. I'd like to start out by kindly thanking our hosts, the Canadian Water Resources Association and the National Hydrologic Service, for sponsoring and for inviting me to speak here today. I'm going to be talking about something called the Canadian Lake River Hydrofabric, CLRH, version 1.0. This is the product of many collaborators, including Brian Tolson, who's going to be speaking later today, Josh Schweeb at Environment Climate Change Canada, and a small army of postdocs and graduate students and undergrad students who helped us out with this over the last few years. And so I'd really like to acknowledge my collaborators here listed here. So, to provide a little background into this work, Environment and Climate Change Canada has spent the last few years developing a updated national hydrometric network data set that is basically a set of shapefiles that represent the drainage areas to all Water Survey of Canada gauges in Canada. This is based on a higher resolution DEM than was previously used, and more importantly, it was based upon a hydrologically conditioned flow direction raster, excuse me, that leads to basins that nearly 100% conform to the National Hydrometric Network, which is the network of blue lines, lakes, streams, and rivers across Canada. Um, in the past, the University of Waterloo and our research group here has done some work in the area of delineating watersheds and subwatersheds. Specifically, a former PhD student here, Ming Han, had developed a cool toolkit called Basin Maker, which was designed for delineating watersheds and subbasins in systems where there's lots of lakes. So that's obviously relevant here in Canada, and it's not very well done by other terrain analysis tools out there. So that is what is unique about this software, and I'll talk about that a little bit more later. We used this tool to develop previously a North American scale lake and river routing product called NALRP, using a coarser resolution DEM and without this fancy hydrologically conditioned flow raster. Um, and we have also used this tool to develop high resolution products for Ontario. So this is an extension and an addition to that past work. So what are these things called lake and river hydrofabrics? Well, at right there is the Lake Nipigon Basin in Ontario, and we can subdivide it into a set of drainage features draining into each other. So these are lakes and rivers draining into other lakes and rivers, and we can zoom in here and this is at high resolution. These are subbasins on the scale of approximately 5 square kilometers, with all lakes included greater than zero point 0.1 square kilometers. And as we zoom in, we have these features, and this is a geospatial data set that's developed at the national scale. So these are data layers stored as shape files, including all of these features, and it also includes a set of estimated lake and river properties like bankfold width and Manning's End and lake depth and lake volume. This is not a hydrologic model or a model output. This is intended to be used as an input for hydrologic models that can be used for things like floodplain mapping or supporting floodplain mapping. So it's really a key input that can be used to build semi-distributed hydrologic models. And this website here, we're going to be opening up a little bit later, and that is where this data set is stored and downloadable. So the goal of this work was to generate a national scale Canadian lake and river hydrofabric for public distribution. So we wanted to be able to do this in support of floodplain prediction. It's intended to be as consistent as possible by the drainage areas produced by the work of Environment Canada, resolve subbasin at these fine scales, include basin outlets at key points of interest. So we reached out and we went across the nation and we gathered all the available provincial flow and level monitoring gauges, the national gauges that are in the HYDAT data sets, and included points of interest at all river crossings along the U.S. border, and ensured that there was a sub-basin outlet associated with each one of these points. And that is so we can have observations consistent with any modeled outputs if we're using a hydrologic model in these systems. We spent a lot of time ensuring that this was quality controlled. We looked at a lot of detailed areas and tried to identify this is not a purely automated process. Uh, my team of collaborators here inspected thousands of individual outlet points to make sure that things were consistent and expected. And our last goal was to distribute this online from the web. So let's look at some of the attributes that are provided here. The CLRH attributes include these subbasins, and every subbasin has information about its mean slope, elevation, and aspect, and also these mean properties for the entire drainage area above that subbasin outlet. We include topological information, which indicates how these subbasins are connected to one another and ensures that we can figure out what upstream and downstream means. We include lake information, things like depth, volume, and the Hydrologic Lakes ID, because this is derived from the Hydrolakes data product produced at the University of McGill. And then we include a bunch of information about channels, again, at the national scale, estimates of length, slope, bank full width, Manning's N. And lastly, we include information about the points of interest that we include in our data set. So what are the benefits of having such a product? Well, lakes are very important across Canada, and so to have a routing network that includes lakes that we can represent all the contributing areas, local contributing areas to those lakes and how they're all connected is very useful, especially given that we're starting to see products come online like the Surface Water and Ocean Tomography Mission, SWOT. It's a satellite mission that's measuring water levels at the global scale. And we can't use these in our models unless we actually have explicit treatment of lakes in said models. And in order to do that, we need to have data products like CLRH, which represent lakes explicitly and the connectivity of the lakes to the rest of the network. A lot of models use gridded simulations where we try to take the irregular world and map it to a rectilinear grid and route water downstream. And that's very hard to do in systems like the one at left, which is an example lake from up north. We try to map this in the direction the water is flowing in a system like this to a regular grid, and we'll have quite a hard time doing that. So to do this accurately, to route water downstream for hydrologic modeling or for in support of hydraulic modeling, we need to have detailed and accurate lake representation at this national scale. So lakes are hydrologically important, so we really need to lean towards this vector representation in our models, and we need the data products that can support that. It's important for more than just modeling, though. There's a lot of people who use watershed delineation information for things like ecohydrologic indicators, stream temperature indices, various forms of risk analysis, determining contaminant contributing areas, salmon spawning, et cetera, et cetera, et cetera. And so a lot of these delineations are done on a per use basis by practitioners. And we have made it easier for them to do these delineations by doing it for them in advance so they can just download these existing high quality watershed delineations. And so we have now a nationwide topologically robust routing network that can promote consistency across applications. Okay, so how did we actually build this thing? Well, first of all, Environment Canada generated this 30-meter enhanced flow direction raster, FDR, for use to generate those station drainage areas. And it's derived from the National Hydrometric Network. And basically what they do is they burn in the network into the flow direction raster rather than the historical approach of burning in the network into a DEM. And that is the necessary ingredient to ensure that we can go down to a resolution like 5 square kilometers. We used that Hydrolakes data set for lake polygons, and we used our Basin Maker software kit. And then a lot of manual intervention to get the details right and make sure that we didn't make mistakes or deal with issues where Hydrolakes didn't agree with the Hydrometric Network and all sorts of confusing things like that. So as I said, that flow direction network is critical here. This burning in of flow directions is a technique that was originally developed by the Ontario MNRF, where we burn the streams into the flow direction raster, and that ensures that the drainage networks are nearly 100% consistent with the NHN vector product that we use to burn in those directions. and it allows us to develop much higher resolutions, finer resolution subbasins. And we're also using a high quality 30-meter DEM. This is the USGS 3-depth DEM. Um, that Basin Maker toolkit, this is an open source software tool. I'm going to show you what it does a little bit later. We can use this for delineating site-specific routing networks, as we have done now across Canada. Its key strength is that proper delineation of lakes. But it can also be used for customization. So we can do things like decrease the spatial resolution of a product from what's at left with almost 1,000 subbasins to what's at right here with just 30 subbasins. So that's very useful. Um, and we can also generate inputs that can directly be used by hydrologic models, such as the Raven Hydrologic Modeling Framework, also developed here at the University of Waterloo. In terms of the workflow, I'm not going to say much here other than it was quite complicated, right? So we broke Canada up into 40 super SDAs, which are sub drainage areas, and these were our work units. And then we had an iterative workflow to actually generate these delineations and put in adjustments and correct for the facts that POIs were not located precisely on the stream and snap them to the correct location and ensure that a point of interest is associated with the reservoir and not the stream directly downstream of the reservoir, et cetera, et cetera. And so this was actually a really complicated process, which required a lot of project management intervention. And so I'll thank Simon and Brian for handling most of that project management. These were the work units that we divided the world up into, our 40 work units. There were some challenges in handling our bigger basins like the Mackenzie and the Nelson, where we started with these smaller units and then we actually have to stitch them together at the end. They were too big to process all at once. We spent time and energy ensuring that we maintained unique subbasin IDs across the entire country. There was a lot of detail work here, which I have mentioned to some degree. There's a lot of confounding issues, like lat long of a point of interest, such as a Water Survey of Canada gauge. In this image at the top right, this is the lat long location of a reservoir. And how do we know whether it's associated with that reservoir? It's not by location because it's not located in the reservoir. It's located somewhere near it. So we need to be able to connect this point to this adjacent lake. And we also run into points, across the border where we have to figure out, okay, where is the border intersection with our stream features? We run into issues with multi-outlet lakes and how do we define a drainage network when we have multiple outlets? When we have causeways and reservoirs and how they're treated in the hydro lakes, they're not necessarily represented correctly, and therefore they're inconsistent with the NHN. So there's tons of different individual issues that we have to deal with, and we're able to mitigate most, but not all of them. Um, but one of the values of this product is that we've done all of this manual QA QC across Canada. And the point I want to make that's really important is that these issues are not handled in existing global scale routing products. So there's a lot of value in handling these specific issues that are unique to specific landscapes. Here's an example of that. This is a lake in the north. I don't know precisely where this is, but this is a place where Hydro Lakes treated this as a single lake polygon based on its geometry. But if we look at the NHN, it turns out that this portion of the lake drains northward and this portion of the lake does not. These are not physically connected. And so we had to manually intervene to ensure that the flow directions were preserved in this lake. So a lot of details here. And there's some benefits to looking into those details. So this is an example here where using the hydro lakes and in conjunction with the NHN, we were able to correctly adjust the missing contributing area, which came from just using lat long alone by connecting those properly. This is a case where we had a gauge at the so this is a polygon here from Hydro Lakes. This is deemed to be a single lake, but we had a gauge at an intermediate point, and it requires intervention. We'd actually have to go in here and split this into two to ensure that the drainage area for this gauge was the actual drainage area. So a lot of places where we've intervened where possible, and where we can't, we note this in the metadata. So this leads to pretty high quality basin delineation. Having a 30-meter product is very useful. And those global products can't resolve smaller basins or respect the drainage network. And this can be seen in our first attempt of making the North American product using a lower resolution to DEM without this burning. We were only able to include about 41% of the WSC gauges, but we now are retaining up to 90% in CLRH. It also handles things like the Welland Canal drainage area, which is impossible to do using conventional terrain analysis. Okay, so let's look at what we have. So this is our current coverage map. As of today, we have over 2 million subbasins containing more than 10,000 points of interest, 400,000 lakes covering 85% of Canada's landmass and most of the populated regions. We've done a quality assessment against Environment Canada's data, and we've took 58,000 of these sites and compared the drainage area delineated by Environment Canada to those delineated within the CLRH. And here, each on the x-axis, these are the 11 major drainage areas. On the y-axis, we have the absolute percent difference in drainage area between the delineated regions, and 98% have less than 10% difference. 93.5% have percent differences less than 1%. So actually, I think this is, yeah. And then almost 80% of them have less than 0.1% error. We're doing quite well in maintaining consistency between these two products. In terms of quality, I'm just going to compare the accuracy of CLRH against a global hydrofabric called Merit Basins. And this is the Merit Basins delineation versus the CLRH delineation. And there are some small differences along the edges due to the use of a higher resolution DEM, which in some cases are important. In this case, probably not from a hydrologic perspective. But one of the most important things is that we have outlets that are actually aligned with the gauge locations. So if we wanted to use this gauge for simulation with Merit Basins, we would not be able to do so with our product is essentially burned in. Some other quality metrics. This is an assessment of CLRH and versus Merit Basins compared to those new Environment Canada drainage areas, and the Merit Basins errors are in the order from anywhere from 0.5% to 161% for this global product, whereas CLRH is on the order of 0 to 0.2%. So we're really respecting the actual drainage areas, or our best estimate of the actual drainage areas of these basins. We've done some spot checks as well. So this is an example of NHN Blue Line Network. And this is, I think, at the south end of Lake Winnipeg. And we looked at the rivers generated by CLRH, and I was like, oh no, what's happening here? There's all these quasi-linear features, and I thought it was an artifact of the algorithm. But it turns out these are actual linear features in the real world that are conveying water, that have their own local watersheds that are respected by CLRH. We would not be able to do this through a DEM-based analysis. Only through this special flow direction raster are we able to capture these features. Here's an example of the shoreline resolution. So this is near Halifax. We do not represent, because we're representing basins, they have to have a threshold of 5 square kilometers. We don't represent all of these coastal basins. They're not included in the product, although they are readily generated by mapping this to a coastal boundary polygon. So that being said, I'd like to stop here, and I'd like to give a little demo of the website. Hopefully I've got enough time to do so. So I'm going to jump out, and we're going to open up the website for the CLRH hydrofabric. And so this is our website here, hydrology.uwaterloo.ca, CLRH. And if we hover over any one of these points, we're going to see the upstream drainage area for that location. And I'm going to type in here, I'm going to go to this top right, and I'm going to go to region 8. So type in region 8 here, and it gives us all of our region 8 WSC gauges. And I'm going to zoom into region 8J specifically and hit zoom. It's going to take us into this region near Prince George. I'm going to close that out, and I'm going to open up one of these sites here. So this is a water survey of Canada gauge. I'm going to click on it here. We have three options. We can download the hydrofabric. We can zoom to the watershed, or we can, in this case, view a demo of what this looks like in ArcGIS Online. And so I click this here. I zoom in. Oh, give it a little time. And this, it's taking its time. This is the lake and river hydrofabric for this region. And so we can zoom in here. Oh,
Can't see the website.
oh, thank you. I don't know why it's not sharing. So let's reshare the application. Sorry. So I wanted to show you that.
I think everybody can see it now. Sorry.
Okay.
Just one person couldn't.
Okay. Glad to hear it. So this is what that product looks like. We can zoom in at any point, and we see this one has, oh, sorry. We can see the data associated with each one of these. All the topological connectivity is stored in here, and we can download this as a shapefile as well. We can also download by region here. So if we switch to toggle regional downloads, and I'm going to zoom out to the national scale, we can download any one of these regions, including the entirety of the Mackenzie. The data specifications are included on this website. And we can also click here and open up a Basin Maker collab, which I'm going to reconnect to here. And this is a Jupyter script, a Python Jupyter script, where we can actually download and process some of the CLRH data. So if I click here, we can install these. Any one of these, we hit play, it will execute the code. You don't have to be an expert in Python to solve this. But we go here to download a gauge level watershed. We type in our gauge ID. We run this, and we can do that at the regional level as well. And that allows us to, by running these code blocks, we'll eventually get to something that looks like this. This is the original product with all of its details. Look at the many, many lakes included here. We can go down further and simplify the routing product by filtering lakes. We go in here as a user input. I'm going to set 5 square kilometer lakes. Everything below that will be removed, and it will redelineate it, and we'll get a product that looks like this. Now all those smaller lakes have been removed, and we can do that, do a similar thing at a threshold here of 30 kilometers for drainage area, and that allows us to get a product looks like this, which we may use for hydrologic modeling purposes or whatever other purpose you have. So lots of other things I'm not going to get into given my shortage of time here. I'm going to return now to my talk. Let me just see. All right. So how can we use this data? We can download this as a map layer. We can use that Basin Maker software on Google Colab with a link to the CLRH site. We can, oh, geez, sorry. This allows us to extract all that data upstream of arbitrary points in the system. It allows us to simplify and clean our geospatial data for use by removing the smaller lakes, by coarsening the resolution, merging subbasins. It allows us to add and remove points of interest, and allows us to generate Raven hydrologic model input files. So there's a whole bunch of things we can do with this product now that we have it. Everyone is allowed to use this. And so here's an example of simplification in a little bit more detail. This is for the Petawawa River Basin in the Algonquin area of Ontario.
James, we're still looking at your web browser.
Oh, geez. So apparently I have to stop share and then reshare. I thought we worked out these technical issues. Right. Okay, are we good now? Thank you. So this is an example simplification of the Petawawa River Basin. We start out with about 1,000 subbasins. We can use Basin Maker to simplify it by removing lakes smaller than 5 square kilometers. We can repeat a similar threshold analysis, removing all subbasins so that we have a threshold of size 50 square kilometers. We can also use this to add or remove points of interest and create hydrologic response units for hydrologic modeling, and then input this into modeling frameworks, specifically the Raven hydrologic modeling framework. All right, so when all is said and done here, we learned a few lessons in this process. We ran into quite a few artifacts from the Hydrologic data product uh, and its consistency with the NHN. So it was common that we'd run into issues like widening of a river or connecting feature between two lakes would be counted as part of the lake. And if there was a gauge at that location, that was problematic. We would definitely benefit from a better lake geometry product. We tried to use NHN water bodies, but that would have required a lot of pre-processing. So we ended up being committed to hydro lakes and just dealt with the issues. We still have issues in the prairies. Our delineations in the prairies are not perfect by any means, but they again respect the NHN. We are handling most of the endorheic areas, endorheic lakes and not major non-contributing areas are embedded within this CLRH product. There's still some open questions in the proper handling of wetlands um, that we'd like to address perhaps in future products. And we learned that there's lots of logistical issues in producing a data set at this scale. We learned the hard way about doing things right. We did things wrong a number of times and had to rewind and put in more QA/QC checks. But we think in the end, all the possible users will benefit from those lessons learned. So to conclude here, we've developed a high-resolution Canadian lake and river hydrofabric with over 10,000 points of interest included, 400,000 lakes, 2 million subbasins covering the majority of Canada. It can support a number of FIMP needs, ECC needs, Environment Climate Change Canada needs, and hopefully NHS needs with regards to hydrologic modeling support. We updated that Basin Maker delineation software. We were able to provide feedback to Environment Canada to improve their national scale flow directions grid and the unreleased version 3 drainage polygons. We have a few minor finishing up steps still needed for provision of metadata and finalizing some minor Arctic drainage areas, but for the most part, it's available for everyone to use. I've got a few references here that I mentioned during the talk, but at this point, I will gladly open things up and take some questions.
Thanks, James. That was great for time too. So I think we could take one question from the Q&A. A reminder to everyone, if you have any questions, please feel free to type them in the Q&A tab. So I have a question here from Tahara Yasmin James. Would the hydrofabrics be used in urban areas for the delineation of stormwater drainage networks? If so, how small would the subcatchment area
Yeah, so
be?
they will not handle correctly subsurface drainage networks like stormwater networks. So this is mostly geared towards non-urban areas and or in urban areas we're dealing with the surface features only. So there will be some discrepancies there.
Excellent. Maybe time for one quick one from Wes. How were river characteristics such as roughness estimated?
So we used a number of empirical relationships from the literature and we've done some testing of those, and in some places they do quite well, and in other places they do less well. And so I'd say they're not by any means perfect, but they are a good start.
Thank you so much. Thank you everyone for your questions. It's helpful if you want to keep typing them out. If you have any other questions to address to James, just to make a note in that so that when we read your questions out later on the webinar, we have that as a reference. Next, I'll move to introduce our second speaker. Dr. Jalbert is a professor in the Department of Mathematics and Industrial Engineering at Polytechnique Montreal since 2017. Their academic journey began in 2003 with a bachelor's degree in engineering physics, where they developed an interest in environmental issues. They then went on to complete a master's degree in water sciences at INRS, followed by a dual PhD in mathematics and earth sciences, specializing in applied statistics for environmental problems. After completing their postdoctoral fellowship in statistics at McGill, Dr. Jalbert began their research as a professor, focusing on climate extremes and applied statistics in climate sciences. We are really grateful for Dr. Jalbert for their time presenting with us today. So I'll hand it over to you.
Okay, thank you very much for the invitation. So today I'm going to talk about interpolation of precipitation IDF curves at unmonitored location using the Canadian Surface Area Analysis product as a spatial covariate. So I should say first that this is a joint work with two of my former master thesis student, Gabriel Gobet, who is now working at ECCC, and also Léo Guillon, and Luc Perrault, who was working at Hydro-Québec. So just to be on the same page, I will just do a quick recap of precipitation IDF curves. So intensity, duration, frequency curves are employed in civil engineering to design infrastructure and ensure compliance with the required safety standard. So here it is an example of IDF curves for the Montreal International Airport. On the x-axis, this is the precipitation duration. On the y-axis, this is the intensity of precipitation. And the different lines here correspond to different return period. So for a design, for example, you need the precipitation intensity that is expected to be exceeded only once in 100 years. For the duration 60 minutes, we can look at the value here. So for Montreal, it should be around 50 millimeters per hour. So example usage of IDF curves are for flood mapping in small catchment and also sizing municipal sewer system, for example. So here, this is the precipitation, the IDF curve that are provided by ECCC, and I will just do a quick recap of how they produce them. So in Canada, the reference IDF curves are produced by ECCC and are available at their meteorological station for 9 duration from 5 minutes to 24 hours. And the estimation procedure is as follows. First, they retrieve the annual maximum precipitation intensity from the data for a given duration. Second, they fit the Gumbel distribution to the annual maxima using the method of probability weighted moment. After they estimate the return levels, so from 2 years to 100 years return level, and this give the x's in the previous plot, this plot, and they repeat independently the procedure for all the remaining duration. And then they perform a power law regression among the x's to be able to trace a solid line in the plot. Those lines that we see here. So here for Montreal Trudeau, we see that the solid lines does not fit very well the empirical or the estimated quantile represented by the x's. Okay. So one problem with IDF curve is that they are only available at ECCC station, which is quite sparse. Originally, the project was to develop IDF curve in the province of Quebec, where we have large dams here. And the current practice was to use the closest IDF curves. And sometimes they might be at several hundred kilometers away. So using that IDF curves do not take into account the spatial heterogeneity of extreme precipitation. So that was the original motivation of the work to interpolate precipitation IDF curves. Okay, so we propose a method to interpolate precipitation IDF curves based on the run from the Canadian Regional Climate Model, driven by a reanalysis as the spatial covariate. It was just to help interpolate extreme precipitation characteristic that we need the covariable to be available everywhere on the spatial domain. So we applied the original methodology on the eastern part of Canada only, where we have access to those spatial covariates. So it was from Ontario to the far east in Canada. We should say also that the spatial estimation of IDF curves is not only useful for interpolation purposes, but it is also allows the sharing of information from neighboring station when we estimate IDF curve. So even if we need a local IDF curves where we have data, using spatial information will improve the precision of the IDF curves at the local station. So then we were financed by some GNC project from ECCC to first change the covariate use for the Canadian surface reanalysis, CAS-R. So we use this surface reanalysis precipitation from this surface reanalysis to as the spatial covariate in our model. The motivation for that is that the CAS-R is available everywhere in Canada, so we could expand our original spatial domain to the Canadian prairies and also British Columbia. So that was the goal of this project. And also, since we have a new spatial covariate, CAS-R, we had to identify the best covariate that we can derive from this reanalysis. Okay, so the data use. So in Canada, we have 589 sites with more than 10 years of data, of recorded data. This is the threshold fixed by ECCC to compute IDF curves. In average, we have 32 years of observation at those sites, which is not a lot. For extreme value, extremes are rare by definition, so 32 years of data, it's very few for doing extreme value analysis. So this is why, again, we can benefit from a spatial modeling. And the data are available from 5 minutes to 24 hours, with, of course, a lot of missing values. Also, as data, we had the Canadian surface reanalysis that is available everywhere in Canada. So we use the CAS-R V2.1 precipitation. So it is predicted precipitation or reanalyze precipitation from 1980 to 2018. The spatial resolution was around 10 kilometers and the temporal resolution was 1 hour. And we use the forecast product, so the precipitation that are given by the meteorological model, and we did not use the product where they did assimilation because we did not want the data to count twice here. So we just need the Canadian surface analysis to have a spatial pattern of precipitation that will help interpolate extreme precipitation characteristic. Okay, so Terry, I just want to do a quick side note, not a side note, but I don't know how to say that on theory here, because this is my main message here. So I want to convince you, civil engineers, that when we work with extreme value, we have to rely on extreme value theory. So I will take a couple of minutes to try to convince you here. Okay, so I will need to introduce extreme value theory. So let's suppose that we have observations that are independent and identically distributing according to a distribution F. And if we take the maximum of the n first random variable, for example, the annual maximum, we have a very strong theorem in extreme value theory that said that under my condition, the maximum converged to the generalized extreme value distribution. So the distribution of the maximum here cannot be approximated by another distribution than the GV. It is the analog of the central limit theory for average. So we know that the the empirical mean convergent distribution to the normal distribution. Here, we know that the maximum converge in distribution to the GEV distribution. Okay. This is quite important because when we have to extrapolate, so for example, if we have 20 years of data and we want to estimate 100 years return level, then we extrapolate beyond the range of the data, and we know by theory that the GV is the only link that is reasonable to do that extrapolation from 20 years of data to 100 years return level estimate. So that's why I'm focusing on extreme value theory here. If you want to interpolate, for example, you have 100 years of data and you want to estimate the 20-year return level, then it is not as important to use the GV as another distribution, but for extrapolating, it is of paramount importance. So in practice, how can we use this theorem here? So in practice, if the block size is large, then we can approximate the distribution of the maximum by the GEV. So for precipitation, when we take a block size of 1 year or 365 days or more, if we look at hourly precipitation, it is usually enough so that the approximation with the GEV is reasonable. So the distribution function of the GEV can be written as follow. The important point here is the distribution has 3 parameters: a location parameter nu, a scale parameter sigma, and a shape parameter psi. And the parameter psi governs the tail behavior of the distribution. So if psi is negative, the maximum is bounded above. So the distribution is bound. So extremes are short-tailed in that case. If psi equals 0, then the right tail decays exponentially, and we say that this is a light tail distribution. And if psi is positive, then the right tail decays polynomially, and this is a heavy tail distribution. So those 3 behaviors are described respectively by the Weibull, Gumbel, and Frichet subtypes of the GV distribution. And with the IDF curves that are currently available and estimated by ECCC, they use the fact that they assume that the psi is equal to 0 and that we are in the Gumbel subtype with a short tail. Okay, so extreme value in practice. This is here the annual maximum precipitation in millimeters recorded at the Montreal International Airport. So what we can do here is that we can assume that each of those points are distributed according to the GV distribution, and we fit the parameters of the GV distribution. So in that case, we had 72 annual maxima that we use to fit the GV, which is not a lot, again, for estimating a 3-parameter distribution like the GV. So the important point here is that our shape estimate here is positive, indicating a heavy tail distribution, which is common for precipitation. We see that everywhere that precipitation are described by heavy tail distribution. However, we cannot exclude the fact that the true value psi might be 0. So this is why some people or some researcher will say, okay, since I cannot exclude 0 from the confidence interval here, I will use the Gumbel distribution instead, and I will have more precision on the remaining parameters. But doing so is dangerous because it is true that the value psi equals 0 could not be rejected, but neither could psi positive. So imposing psi equal to 0 would ignore the genuine uncertainty in the tail behavior inherent in extreme value modeling. So in extreme value modeling, since we extrapolate from data, we have to live with these large uncertainties. And if we want to reduce this uncertainty, we have to do spatial modeling or other technique. Okay, this is the example with the Montreal Trudeau precipitation. So here it is the fitted GV that fits very well the data, and we can compute the 95 confidence interval, and we see that the model fits very well the data. So we assume that the block size of 365 days is large enough for the model to be good here. If we fit the Gumbel distribution, this is what we obtain. So we fit the Gumbel distribution. It is not a bad fit, but it is clearly not a good fit either. So when we look at the very extreme precipitation, the Gumbel model underestimate the extremes, which is expected since the Gumbel distribution is light tail and precipitation data are heavy tail. But more dangerously, we clearly underestimate the uncertainty. So using the Gumbel distribution is an error here. So that was my speech to use the G. Okay, so now methodology. We want to interpolate IDF curves. So I will present succinctly the methodology here. So the spatial modeling of extreme precipitation is performed independently for the following three regions of Canada: east of Canada, prairies, and British Columbia. And also we interpolate independently for each duration. This is because the spatial covariate that we use and their size effect can vary across different regions of Canada and duration. So that is why we did that. So the model that we propose consists of a Bayesian hierarchical model. It is common also in spatial modeling. So the first level of the model consists of a GV distribution that model the annual maxima that are recorded. The spatial layer or process layer model the spatial variation of the GV parameters among the spatial domain. And we should say that this is in that level that it enables information sharing across space. And also, this is in this level that we are able to interpolate at sites where we don't have observations. So the data layer, it is GV distributions. So it is assumed that each annual maxima of year J at station I is assumed to be distributed according to the GV distribution, where the location and scale depends on the location where we are in the spatial domain. But we assume that psi is unknown, but it is common for all stations on the spatial domain. So the key points here are the GV models the annual maxima at each station, and information from all stations in the spatial domain is pooled together for estimating psi. So in the process layer, so the spatial variability of the GV location parameter and scale parameters are assumed to vary spatially following a linear relationship with the spatial covariate that are CAS-R precipitation here. So we will use a regression like in the process layer to explain the spatial variety in the GV distribution. So here X represent the CAS-R precipitation or the CAS-R derived covariate that we use for the location parameters, and UI here is a spatially current error. So if at the station we have a positive discrepancy between CAS-R precipitation and the record precipitation, it is more likely to also have positive discrepancy around these sites. So this is how we model the spatial dependence here. And the range of these dependence will be estimated with the data. Okay, so the key points here is the regression corrects for any bias introduced by the spatial covariate. So here we use the predicted precipitation, which is not the product with assimilation. So we maybe have a bias, but it is not important since we use that in a regression. So we kind of like correcting the bias directly. But one thing that is important is that we have to find the best set of spatial covariate to be able to explain these spatial variability in the GV parameters. And it is in this layer that we can perform spatial interpolation of GV and after IDF curves. Okay, some results. So for the east of Canada, this is the region where the project was originated. So we did a lot of validation of IDF curves compute on that region. So we found that the significant spatial covariate is the average daily CAS-R precipitation, which is here shown here on the figure. So it helps to interpolate the GV parameters spatial variation. So we found that extreme CAS-R precipitation are less powerful than the average for the spatial interpolation of GV parameters, which was a bit surprising, but it is something that we find in the literature also, that the extreme precipitation interpolation can be achieved using the daily, not the daily, sorry, but the mean precipitation. And also an important thing is that the GV shape parameters is significantly positive, indicating a heavy tail. So when we combine information from all the station, then the confidence interval on the shape parameters does not include 0. So we are positive that this precipitation are heavy tail here. Okay, so here this is a map of the 100-year return level in millimeters for the 24-hour rainfall accumulation. So for compute IDF curves, we would have to repeat this analysis for the other duration. So the 8 remaining duration from 5 minutes to 24 hours here. And then we would be able to compute IDF curves everywhere on that spatial domain. Okay, so here in east of Canada, what we did originally, we did a thorough leave one out cross validation. So for each of the stations that we have in the spatial domain, we remove one station, we fit the model, we try to predict the IDF curves, and we compare it with the real IDF curves. So here again, I took the data from the Montreal International Airport, which is the station that are closest to my home. So this is the local model here. It is the GV fitted with the actual data. And if we look at our interpolation, so if we remove those data and try to predict the GV, this is what we obtain. It is not perfect, but it is not bad. Also, if we add the confidence interval, we could see that our uncertainty covers those points here. So it is quite good, and most of the time we improve the interpolation in contrast to the usual approach of using the closest IDF curves, where we don't have at site where we don't have observation. So most of the time we improve in contrast to the naive approach of taking the closest IDF curves. Okay, so for the prairies, we also did the interpolation for the Canadian prairies. So again, the story is practically the same. So the significant spatial covariate is the average daily CAS-R precipitation. Again, extreme CAS-R precipitation are less powerful than the average for spatial interpolation. And again, the GV shape parameters is significantly positive, indicating a heavy tail distribution. And now we can look at some results for British Columbia. This is a bit different here. So the significant spatial covariate for the British Columbia is the average daily precipitation and the extreme CAS-R precipitation and the station elevation. So we have three significant covariates here. We still have something to adjust here because we have to give some spatial attention to station with large difference in elevation between the mean elevation of the grid point of CAS-R and the station. If a station is near the ocean, but the elevation of the grid cell of 100 square kilometers is higher, we have to correct that discrepancy in elevation. So we still have to do some adjustment here. But again, the GV shape parameters is significantly positive, indicating a heavy tail distribution. So in conclusion, so the results indicate that the spatial information in CAS-R can be utilized to interpolate the characteristic of extreme rainfall, and we can use that to construct IDF curves everywhere in Canada. So a thorough cross-validation study is still ongoing for the two remaining spatial domain, British Columbia and the prairies, but for the eastern part of Canada, that is done. And also we have to do some spatial attention to station with large difference in elevation between the CAS-R grid cell and the station. So limitation and ongoing work. So at this point, spatial interpolation is conducted independently for each duration. So for 5 minutes, 10 minutes, 15 minutes, etc. We did the interpolation completely independently, but we have ongoing work on focusing on jointly interpolating the IDF curves of the 9 duration at once. We are also evaluating the combination of 3 spatial domains into a single statistical model for a single model that would be easier to use. So instead of partitioning the Canada into 3 spatial domains, we will try to regroup that in one spatial domain. And we finally are developing a method to incorporate climate change effect into the interpolated IDF curves across Canada. I hope I keep the time okay.
Thanks, Dr. Jalbert, for sharing your insights today. Just a reminder, and I've already seen a couple come in. If you have any questions for Dr. Jalbert, please type them into the Q&A tab. It helps us keep track of them. We'll have time for maybe one question. So if you can just make sure you're typing out that the question is directed to Dr. Jalbert, we'll get to them. We'll have more time for questions at the end of the webinar. So I'm going to merge these 2 questions. They're from an anonymous attendee, and they ask, how do you calculate return periods and how often do those values change? And how many years would we ideally want for an extreme event?
Okay, so how many years? It is not an easy question. I will go back to my main message here is that use the GV distribution. So with the GV distribution, we can extrapolate. So if we have 20 years of data, we can extrapolate to beyond the range of data. But of course, it will be very uncertain, but it is normal since we extrapolate. So we don't have a limit. Yeah. And what was the first question, Sam?
First question, how do you calculate return periods and how often do those values change?
Okay, return period depends on the application, I think. So civil engineers, which I'm not, they have they have law requirement or something like that to say that I don't know, for a sewer system they have to use 20 years return level. So my job is just to provide the return level, and I'm not able to decide on the return period.
Thank you so much. As I mentioned, we'll have some more time for questions at the end of the webinar. Our third and final speaker is Dr. Brian Tolson. Dr. Tolson is an expert in calibration and optimization of hydrologic and water resource models. He has more than 20 years of experience building and calibrating surface water and water infrastructure models all across Canada. Dr. Tolson was the developer of the dynamically dimensioned search optimization algorithm used by ECCC, U.S. National Weather Service, and others to calibrate their hydrologic models. He is a co-developer of Basin Maker lake and river routing network delineation software used by his team to generate large-scale model agnostic lake and river routing products, such as the Canadian Lake and River Hydrofabric and the Ontario Lake and River Routing product. Brian is also a key collaborator on the Raven hydrologic modeling framework mentioned earlier and Casper archive of ECCC's numerical weather forecasts. His diverse research expertise and interests span across hydrologic machine learning applications as well as hydrological forecasting. We're super grateful for Dr. Tolson for his time presenting with us today. Without further ado, over to you.
Thanks, Samantha. Sorry for the long intro for everyone.
All good.
I presume you can almost see my slides properly. Let me swap that. There we go. Okay, so I'm presenting today largely because the lead author on this work, Glenn, he's on parental leave, so he's not able to present. But I'm really pleased to be able to present this work on behalf of a team that worked together.
Brian, French slides are up. We're just waiting for your version.
Oh, I didn't share my slide. Hang on, let me make sure I share my screen.
Okay, no problem. Take your time.
And I thought I had this down, but why would it?
Okay, and then we're gonna swap. Excellent. All right, that's great.
Everybody's on board here. Okay, there we go. Sorry about that. So yeah, so I'm presenting on behalf of a big team. Much of what you'll see today is how Glenn put together a couple of distinct research outputs from our team over the years. And so without Ming's work and Julianne's work and James's work on their software and tools, we wouldn't have been able to do this today. So I'm going to talk about enhancing an LSTM-based streamflow prediction system with a spatially distributed approach. So the research questions we had when we started this work was, first, how can we effectively account for spatial variability when building LSTM-based deep learning models of streamflow in large basins? And when I say large in this presentation, I'm going to talk about basins over 2,000 square kilometers. And then the second question is, if we can do that, does the implementation actually remain generalizable, enabling prediction in ungauged basins? And so we think that the work in Glenn's paper last year was the first study that really answered those questions. So some background to sort everybody out here before I get into the results and method. Most of you know that when we build a model of a watershed, we can build it in lumped mode. Lumped mode is when everything's just one input and one output. Semi-distributed mode would be maybe when you have subbasins and break this into a vector network of subbasins. And then some people call distributed modeling when you break it into grids. Probably most people would say that this is not real. This is just a gridded model, but a real distributed model would have a very fine grid on the order of maybe 30 by 30 meters or something like that. So these are the three types of ways you can break up a watershed and model it. And so when you think about LSTMs for streamflow prediction, I would say that the current standard for LSTMs and streamflow prediction are pioneered by Kratzer et al. Their group in 2018 really led the way, I think, in this area. But LSTMs are essentially a type of recurrent neural network. And these are used to build large regional scale models of streamflow. They're suitable for time series analysis, and because they really capture temporal variability and dependency of the various input variables that they're trained on. Now, the key here is with LSTMs, each basin is basically an input data set, or each basin in the input data set, I should say, is an instance consisting of input features or explanatory variables that are spatially aggregated to the basin scale. And because these LSTMs aggregate to the basin scale, they're by definition a lumped model. Now, numerous recent studies have shown that regional lumped LSTMs are, unfortunately, in my view, better than traditional physically based or physically inspired hydrological models for streamflow prediction. Now, we've seen that that's true in gauged basins, but also even more true in ungauged basins. We've seen that in comparison with traditional lumped physically based models as well as semi-distributed models. Doesn't quite matter how you compare. These lumped LSTMs, they're just really good predictors of streamflow. It's also worth noting that there's a ton of large sample hydrology sets out there, hydrology data sets out there. And so with those large sample hydrology data sets and current LSTM software being produced, like the neural hydrology package, it does make modeling streamflow with AI sort of easier and easier. And so in this presentation, we're going to rely on using the neural hydrology package in our LSTM modeling work. So just to show you, this was a great study that Julie led back on comparing various models for streamflow prediction in the Great Lakes Basin. And this table is showing essentially validation KGE. So this is sort of like Nash-Sutcliffe. Maximum KGE is 1.0. We'd like to have all our models as close to 1.0 as possible. 0.8 is usually very good. And so here's all of the validation performance in this model intercomparison study across 12 different models in the Great Lakes. And so we have temporal validation, spatial validation, and spatial temporal validation at dozens and dozens of stations here. And the best GRIP-GL model that was physically based or not AI, we calculated the median KGE in all of these categories. And the median KGE of the best model was worse than the lumped LSTM KGE in all of these validation modes. And in particular, very big differences in spatial validation and spatial temporal validation mode. 0.16 on a KGE scale of an improved model is pretty substantial, I would say. So what does this mean? It means that our lumped LSTM in this study was beating models like HiMod, GR4J, VIC, SWAT. Many of these were implemented in Raven, as well as the mesh model and other things. And so, before this study, I wasn't necessarily a believer that machine learning or AI was a good streamflow predictor. But after this study, I was, because there was one AI team building the lumped model and there was 12 physically based modeling teams building the other ones, and these were the results. Okay, so LSTMs work, lumped LSTMs work, but even though they're excellent, it somehow nagged on me that these things neglect the spatial variability of the inputs within each basin. So realize that these are lumped models. And what we did look at when we really drilled down into some of the GRIP-GL basins, some of the larger ones, the LSTM was actually failing and it wasn't working well at all. So we wanted to improve that. Unfortunately, when you build LSTMs and you have gridded data sets like a gridded precipitation product overlaid on the watershed here like you see, we get these different spatial patterns of precipitation. And the LSTM just calculates, for the LSTM model, we just calculate an average of these grid cells over the basin. And so that didn't seem like we were missing something. And so an architectural limitation of LSTMs, though, means that they aren't built to be compatible with this kind of gridded level, sub-basin level raw input data. So they're really built as and easy to use as lumped tools. And so prior to our work, I would say that no one had really figured out, that I was aware of, how to make quality LSTM predictions for streamflow in large basins. So we wanted to see if we could change that. So we built something called a spatially recursive model, or SR model. And there's three different components or modules in the SR model. First, there's a trained lumped LSTM. So this is basically a regional model that's trained and regionalized for streamflow prediction in your region of interest that you want to model in. The second thing you need is a delineated lake and river routing network. So something like CLRH, like you saw from James Craig. And this would discretize each of your basins of interest into smaller subbasins. And the third thing you need is a hydrologic routing-only submodel. So this is meant to be a process-based hydrologic submodel that basically moves water between the subbasins and between any lakes in your routing network. Now, some of you might be wondering why we're calling this a spatially recursive model, and I think we settled on that originally because that terminology is essentially meant to imply the application of an LSTM to subbasins or spatial scales that are smaller than the typical basin size in the training data set. So that's why we thought of it as a spatially recursive sort of approach. So for each basin, our SR model basically considers the spatial variability of the input variables at a finer resolution by having a smaller response unit. So how does this work? Okay, let's consider we have a basin of interest here. We're going to apply our SR model. The first step is to employ a pre-trained lumped LSTM, and that's going to predict local stream flow in the subbasins. And so you can see this is what we're going to do at these red triangles. So we got our complicated AI model predicting at each subbasin, and that's going to generate a hydrograph, and those are going to get input to our routing model at the triangular locations. Those are instantaneous stream flows from the local subbasins. Those are inputs to the routing model, and then the routing model in uncalibrated mode basically just simulates the water movement between the subbasins and through various lakes to ultimately predict the discharge at the outlet. Okay, and if we use an uncalibrated routing model, then we think that this is applicable to ungauged basins. So again, the lumped LSTM literature is only focused on predicting outflow stream flow here, whereas we're trying to predict it intermediately to, in essence, to build a better outflow prediction. So I'm not sure that I love the spatially recursive terminology of the model that the name that we used for our model. So I wanted to introduce some alternative names so people are not confused about what we're actually doing. So we could have said that this is a spatially distributed streamflow prediction approach using an LSTM. We could have said this is a hybrid streamflow simulation model. This is an LSTM plus a physically based lake and river routing network and model. And so I just wanted to put those alternative names out there so you can make sure that you understand sort of what we're really trying to do and don't get stuck on the spatially recursive terminology. So the tools that we use for each component here in the SR model builds on all of our previous work in this research group. So the first thing is we started off with the GRIP-GL project case study, which provided us case study subbasins and a trained lumped LSTM built by somebody built prior. The second thing is we used our Basin Maker toolbox to give us our delineated lake and river routing networks that we need and help us generalize. And then the last thing we need our routing only submodel, and this came from the Raven modeling framework that James pioneered. So what does the GRIP-GL model do? Well, it produces a trained lumped LSTM that we use. It predicts local subbasin stream flow at the subbasin outlet. It's not the stream flow from the upstream subbasins. It's just local stream flow. And we run this at a daily time step. And some of you might be wondering what we use to predict with the LSTM. Well, there's 9 dynamic basin attributes that we would get from CASR, for example, the CASR version 2, as well as 30 static basin attributes. And I can talk about those at the end of the presentation if people have questions. They're certainly in the extra slides bit. The second component, the lake and river routing network, we need this because this defines the connectivity between our lakes and rivers, channels, and subbasins. This provides us with default values that we need to run a hydrologic routing model. Essentially in this work, you'll see that we use 3 different distinct Basin Maker routing products here to demonstrate that this works, and it works with all 3 of them. The last bit is using Raven in routing only mode. And so some of you who are Raven models will appreciate the conciseness of this RVI file, which controls what processes are simulated in Raven. This is how short it is. It's configured to run in routing only mode. And again, we get default routing parameters from our routing product. We run Raven with the diffusive wave option for in-channel routing. Our natural lakes are simulated with the broad-crested Weir equation with an assumed width from our routing products, routing networks. And then essentially we input local subbasin stream flows as precipitation to the model. And we can run this routing at an hourly time step, not at a daily time step, even though our forcings are at a daily time step. So for experimental design purposes, we really looked at performance based on KGE. Again, that's like a Nash-Sutcliffe, negative infinity to 1. 1 is the best value. We basically said that our lumped LSTM is our benchmark model for comparing our new model results to. We wanted to see if we could improve upon that. And then in all experiments, I want to emphasize that each module of our SR model is at its original or default state. There's no retraining. There's no fine-tuning of the LSTM for use within our model. There's no calibration of the routing model subparameters, routing submodel parameters. So we didn't do any fine-tuning to make this work. We just tried it. So we had 2 regional case studies. The first one is the great GripGL case study that I'm going to talk about. That's what we actually published on. The second one is in the Fraser River basin of British Columbia, and we didn't publish on that actually. So when we compare the SR model versus the LSTM model, we do it first in GripGL validation basins. The second thing we do is we do true out-of-sample testing. We basically found 8 new gauges in the GripGL region, but they weren't used in the GripGL study. So we saw how the lumped LSTM versus our model worked. And then in the Fraser Basin study, it was basically an out-of-sample test on the entire methodology because we used an entirely new LSTM, we used an entirely new routing product, and just tried it to see if it generalizes and works pretty well. In terms of the study that we did, so the first case study was GripGL. Our training basin histogram here is shown in terms of drainage area sizes. And so you can see that we had training basins ranging from roughly 200 to 20,000 square kilometers. And so when we tested with this case study, our testing range was in the same range, but actually went to 0, essentially. We tested to see that we could do this in small basins too. In the other case study, you can see that our training range was limited to small basins only, so 0 to 2,000 square kilometers. And then we wanted to test to see how well these things worked if we applied them for only large basins. So those were our 2 strategies here. So first of all, the first experiment was to say, can the LSTM predict reasonable stream flow at spatial scales that were below the training data? In GripGL, we didn't train the model with basins less than 200 square kilometers. So here we looked and we wanted to see if the LSTM could extrapolate in lumped mode to smaller drainage areas like 86 and 95 square kilometers. And you can see based on these hydrographs that these are not fantastic necessarily hydrographs, but they predict reasonably well. So the answer is yes, we think that the LSTM can extrapolate towards smaller basins. So now let's look at the results here. This is the table that we saw before, okay? This is the validation performance in different spatio-temporal through temporal validation. And here's our lumped LSTM results. And again, in GripGL, all we did is we said, let's apply the SR model with everything from GripGL. Same study results, the same data, same LSTM, same uncalibrated routing networks, and see what happens. And when we do that, you can see that for drainage areas over 2,000 square kilometers, we're having some pretty good improvements to the median KGE over the lumped LSTM. So that was nice to see. Importantly, if you compare what happens between the lumped LSTM and the SR model for small basins, there's not really a big degradation in quality of results here. So we didn't break anything by doing this, let's say. So that was happy. We were happy about that. And if you look at the hydrographs here, these are just focus on the hydrographs. These are basically the two basins that showed the most significant improvement, relative to our lumped LSTM. So the red is our lumped LSTM hydrograph, which was a total failure for this massive basin. And when you apply the SR methodology to it, that's the blue line, and you can see that the blue line tracks the observed discharge quite well, KGE of about 0.8. Same thing over here, slightly smaller basin, but again, the lumped LSTM was failing. And we get not a great fit, but it's a much better fit with the SR model. So that was good. I'll skip this slide here. This is just showing like the best performance that we saw from the SR model in relation to the lumped LSTM. And basically you can see that the blue hydrographs are much better than the red hydrographs. So the second experiment, we said, okay, let's get 8 brand new basins that we had never modeled before with in GripGL and just see how things go. We reused the GripGL LSTM regional model. We just reapplied it. And then we reapplied essentially a similar type of subbasin or lake discretization approach that we used in GripGL, except there was a difference here. We actually used our North American routing product, routing networks instead. So this was a slightly revised version relative to the original work in GripGL. What we found is if you look at the 8 stations sorted from smallest station over here on the left to largest station over here on the right, the red KGE is this axis, and red is the lumped LSTM, blue is our new SR model. And you can see that there's some very big differences between a lot of these blue and red bars. Some of these are 0.2 or almost 0.2 on a KGE scale better when we use the SR model. So not always better, but there's just this one where it's not. And so good results here. Really happy with this result here. And that was published in the paper as well. So this new result is not published in the paper. This was going a bit further, applying this whole methodology to a new case study with a new LSTM, new routing networks, really want to test generalizability. So first we trained a new LSTM for the Fraser River Basin, only on natural basins. It was an LSTM that was new because we were actually considering things like glacial area and geopotential as static attributes. The basin areas ranged from 5.6 to 1,900 square kilometers. And then we wanted to confirm that the lumped LSTM performance was actually good. Median KGEs in spatial temporal and temporal validation were actually pretty good here. We were quite happy with the LSTM in lumped mode. And just as a comparator, we built some Raven models in this case study as well. And our temporal validation performance for Raven was slightly less than the LSTM temporal validation performance. And so, again, just evidence that we built pretty good quality lumped LSTM models. And now we want to see if we can actually improve on those already good results. The second step was to delineate our lake and river routing networks. And for this, we utilized the CLRH product that you saw from James earlier in today's talks. And basically, we just adopted discretization decisions from our previous Raven model applications there. So we didn't fine-tune anything. We just did what we had done in another case study to see what works. Then we combine the routing networks. We combine the LSTM and push them through Raven in the routing-only model. Again, broad-crested weir, diffusive wave option, hourly time step. So the results here, looking just at 4 basins in the Fraser. These are big basins. They're natural. I think they are natural. They are natural. Some of them had no lake. One of them had no lakes. Others had lots of lakes. And you can see that the lumped LSTM works okay, decently, I would say in validation mode for sure for these 2 slightly smaller basins, but the larger basins, it fails. It doesn't work. So when we just apply our spatially recursive model, you can see that we get some massive improvements in these relative to the lumped LSTM. So on the order, again, of 0.2 kGe increase or more in all of those cases. So that was really heartening to see. So in conclusion, I think that incorporating spatially distributed inputs really does improve streamflow prediction in large basins, so large being 2,000 kilometers squared or greater. The SR model that we built is demonstrated to be generalizable for prediction in ungauged basins. It's generalizable in that the model predicts well without the need for further fine-tuning, parameter transfer, or parameter calibration, given that you have a lumped LSTM trained for the region, and given that you also have a routing network. Some additional benefits that we didn't emphasize in our publication originally that I think are really beneficial to note in practice for folks. First of all, our approach gives spatially distributed streamflow predictions across the basin. We didn't leverage that or even talk about that very much, but that's definitely one of the natural outputs of this approach, which is very useful. The other thing is we end up generating hourly hydrographs, but we don't need to train an hourly time step LSTM, which is super useful. And the last
Brian,
thing,
sorry to interrupt. I'm just checking in here. I know you have a demo. So just for time, I'm not sure if you want to jump ahead to the demo.
Yep, that sounds good.
Okay, go ahead.
So then the last thing is just looking at, Raven can be used with extensive water management tools. And so if you build a Raven model like that, you can easily plug and play sort of an LSTM into that, combine Raven and water management mode with that. So the demo here, I just wanted to show that we have a GitHub site demonstrating the software that we did to put this all together. And if you go to this demo, I'll just show you, maybe Hannah has Hannah might have a link to this website, but this is just our demo model results viewed in Raven View. This is a tool that James put together, but you can see the predictions here and the fact that we have hourly predictions in blue versus the observed daily results here, and the fact that this is spatially distributed. We get a hydrograph simulated at every one of these subbasins. And since this is a routing model that has reservoirs, lakes, natural lakes, we also get all of these lake levels, lake stages simulated as a result. So it's really powerful from that perspective. So you can play around with this website if it goes in the chat if you want to. I will go back to my slides and finish up. I think you can see them now. So just a few notes, boring notes on how you can get to this GitHub website and what it does. Essentially puts together an example. So it shows you how to put together an example of the SR model with all of our tools. And since we published it, it's become faster. We've made it a bit more efficient. So future work, we want to demonstrate performance of the routing only of the whole modeling system when we calibrate the routing model. We want to look at quality of subdaily predictions, enhance Raven to more seamlessly work with an LSTM. And again, we're interested in doing this, trying to apply this SR modeling framework in other regions in Canada. So all in all, there's a ton of collaboration opportunities. If people are interested, we're open to it, and I think we've got more ideas that we can handle. So happy to talk to people if they're interested in collaborating on using any of these tools. And just thanking the support from the FHIMP program. We also had support from Global Water Futures. So thanks very much.
Excellent. Thank you so much, Brian, for your presentation. Just a reminder again, if you have any questions for Dr. Tolson, please type them into the Q&A tab. So I will take one question I see here from Brett for Dr. Tolson. Do you think that if we could just improve the inputs into a single LSTM, for example, providing additional inputs about the subbasins, it would outperform the SR model?
I think that no, I don't think that a hydrologist could do that for sure. Could a machine learning or AI person do that? I mean, maybe, but the issue is that you have to respect the spatial variability of the inputs. And so the easiest way to do that is with a vector-based approach, and encoding a vector-based approach into an LSTM sort of framework just doesn't work. It's just not built to handle, multiple instances of the same input. And so, and it's hard to generalize that. So I actually don't think that that's that possible. And if it is possible, I would assume that it would be very hard for that model to outperform the SR model, especially if the SR model we were able to calibrate the routing model parameters, which we don't.
Got it. Okay. Thank you so much. And we're doing great for time. So now we're going to move into a panel discussion. And I'll invite Emmanuel as well as all speakers to turn on their cameras for this part of the webinar. We've prepared a couple questions for the speakers to learn a bit more about their work and then to prime our Q&A. So please keep the questions coming. If you'd like to address the questions to all speakers, include that in your typed answer. If it's a specific speaker, please denote that in your question. I'm going to hand it over to Emmanuel first for her question.
Great. So the first question is, how is climate change affecting the accuracy and reliability of your work? I don't know if Dr. Jagbayev or Craig want to start to give Brian a 2-minute break.
Yeah, please.
Well, I've got the easiest version of this because for the CLRH work, that is all spatial. We don't expect our waterways to be changing significantly due to climate change, hopefully. So for the CLRH, we don't expect much adjustment at all. In the near future, maybe 50 years from now, things will start to look different as permafrost melts and new channels are formed and lakes dry up. But for now, we can consider that stationary.
Yeah, from a statistical point of view, it is true for IDF curves too, because the natural variability of extreme precipitation currently obscures the climate change signal. So extreme precipitation are very, very, very variable. So, and it is natural, it is normal. So it's hiding actually the climate change signal, but we know that there is one. We are just not able to detect it statistically. So if we had more longer series, we would be able to detect it. But for now, we cannot on actual records, at least for precipitation. But when we look at simulated precipitation from climate models, we have a longer series, and then we see that there is, without a doubt, climate change impact or effect on extreme precipitation. It is just that right now, with actual data, we cannot see that or find it significant.
I guess I'm supposed to answer this too. So there's a lot of work that I'm not involved in that's being published on the ability of machine learning and AI tools to predict extremes. And what I'm seeing, in general, I think that they can predict unseen values that didn't get put into the training data set. And so I actually think that there's some real potential to use machine learning tools to predict the impacts of climate change on things like stream flow. I'm not convinced that won't work. I think some people are, but I'm seeing papers come out that are convincing me that they are good extrapolators and they could be okay for that purpose.
Kind of a more to come answer. Yeah. So my question again is going to address to all speakers. Many municipalities and policymakers do struggle with outdated or coarse resolution flood maps. So in your expertise, how can practitioners integrate your findings into hydrologic modeling and flood hazard mapping? Let's go in the order of presentations again.
Well, hopefully it was reasonably clear how you could see how the data sets that we've generated, such as CLRH and the tools like Basin Maker, could be useful in a hydrologic modeling and a hydraulic modeling environment. I mean, that's what they're designed for, right? They're designed to provide the hydrofabric underneath which these models sit, and these models actually require it in order to generate high resolution stream flow predictions, which can then be used to inform flood models. So there is an extra step there that we have to connect those models to hydraulic models of some type in order to estimate floodplain extents. And but there's a pretty clear connection. So we provide the hydrofabric by which that can be connected to hydrologic models that can inform the upstream boundary conditions to flood models is the sequence that I see happening.
Thanks, James.
So I'm not an expert in hydrology or flood zone mapping or stuff like that. I'm an extreme value statistician. So I think that we have to work in teams because I have the impression that extreme precipitation can be used in hydrological modeling, but I cannot do that because I'm not an expert on that. But I think that the more knowledge that we have on extreme precipitation could in fine lead to more detailed flood zone mapping. At least it's my hope.
So I can actually help Jonathan out here with this. The estimates of extreme values of precipitation are critical inputs to the models that are used to generate estimates of extreme values of floods, which determine the extents of floodplains. So getting those statistics right and reducing the uncertainty in their projections is a critical step towards reducing the uncertainty in our floodplain predictions. So again, very directly connected. Whether you're a civil engineer or a statistician, we can all work together.
Yeah, I would say if I can first kind of augment James's answer on the CLRH work that we did. I don't see why that wouldn't be a valid starting point for anybody that's trying to delineate a floodplain. You don't need a LiDAR data set to determine the watershed boundaries. You need something that follows the drainage network, and our product follows the drainage network. So I think that's an excellent starting point for people to build the models to produce the boundary conditions for floodplain modeling. And then for the floodplain modeling itself, you would want to use more high resolution data sets. So I think CLRH is a great starting point for anybody who wants to do hydrologic modeling in Canada. In terms of the SR model that we did, I mean, I guess the interesting thing there is that it provides one way to move from daily predictions, which many of us build models to do, down to hourly predictions. Now, we still are evaluating the quality of some of those, but it might be useful in some basins to be able to have that ability to directly look at hourly flow statistics in ungauged basins rather than daily. So I think that's one avenue making use of that. So
Brian, I'm going to back you up on this too. I think there's another argument that the quality of the LSDMs outperforms that of many of our physically based models, especially in estimating in ungauged basins. So when we need to do hydraulic predictions in ungauged basins, the SR method is a means by which to basically regionalize those high quality LSTM predictions to determine peak flows in places where we don't have direct observation of those peak flows, which again is a necessary input to hydraulic models, which are used for floodplain delineation. So,
thanks.
Yeah. No problem.
Thank you to all the speakers. I'm going to move, unless there are any other comments amongst the panel on that question, we're okay to move into our Q&A period. So I noticed that in between presentations, our speakers were very diligent in typing out answers for a lot of our questions, and thank you to our audience for submitting those questions. A few that are remaining. So this question from Abhilash to Dr. Craig: how does the CLRH integrate with the Raven hydrological modeling framework, Basemaker tools, or Hydrologic software to improve the accuracy and efficiency of hydrological simulations?
So I would say it doesn't necessarily improve the efficiency of these models. It can improve the accuracy by providing a solid backbone upon which the models are built, right? So getting drainage area correct is one of the most important things for a model to provide a accurate prediction. Inaccurate drainage areas lead to inaccurate predictions. So that's what we're providing is that connectivity of the network, proper drainage area estimation, proper characterization of lakes and river networks that are inputs to our hydrologic models, and hopefully with those better improved inputs, we get improved outputs.
Thanks, James. And I did see a hand show up, but flashed. I don't know if the person lowered their hand. But during the Q&A period, which reminds me, if you do want to ask your questions live, please use the raise hand function, and we'll be able to allow you to unmute and ask the question live to the speakers. In the meantime, I'm actually going to move to a question that, Jonathan, you've typed out an answer to, but I'm hoping maybe you can elaborate on it a bit more. So I'll read out the question from Hisham. When conducting the interpolation and extrapolation of precipitation data between stations, should there be criteria to select catchments within the same climate zone and physiographic location, catchment sizes to appropriately predict at the ungauged locations?
Yes, it could be very useful if we want to compute discharge from a watershed with the rational method, for example. But for precipitation, since we use a spatial covariate that are derived from the CAS-R surface reanalysis, so we think that most of the physical variables are included in those precipitations. So for only precipitation, I think we don't need the information on the catchment into the model for interpolating precipitation.
Thank you. And then I'm going to stay on you for another question from Hattie. And you've typed out an answer, but I'm hoping you can elaborate on this for the other attendees. How do you plan to integrate the effects of climate change into the interpolated IDF? A little bit connected to Manuel's question, but do you consider climate change to be a linear phenomenon in this context?
Yeah, I don't expect climate change to be linear. What we are doing right now with several students is to estimate IDF curves from climate model simulation with their different greenhouse gases scenarios, and we will try to match the signal that we see in the simulation to the actual IDF curve that we are estimated and everywhere on the spatial domain. So maybe we are thinking about a post-processing procedure, a statistical post-processing procedure to match those two data sets, but we are not yet ready to share our results. But this is the idea that we want to do.
Thank you. I have a question here. I believe this is for Dr. Tolson from Jonathan Wilkie. I find that all models miss the magnitudes of extremes in the reanalysis, particularly for basins dominated by rain, making it difficult to use these types of models to estimate future flows. Has the performance of this model at the extremes been evaluated?
Assuming this is for me and for my SR model, early in the project we were looking at that. We didn't do a complete job looking at only peak flow estimates. So I would say that's probably to come.
Thank you. And then Charles provided a very helpful resource in here on LSTM. But if you could
Thank you.
speak broadly, Brian, just for general folks who aren't familiar with LSTMs, can you explain a bit further how that operates?
Well, I'm not an expert in LSTMs. I use them because they work. But I always think of them as a complicated regression model. But the most important thing about LSTMs and AI and hydrology is that they are built and trained to be both at site and regional predictors at the same time. So you don't build an LSTM for a single basin. At least you don't do it if you want to do it. Don't do that if you want to model properly. You build an LSTM to 100 or hundreds of basins, and the LSTM learns in the training process, not just the specific at-site parameters within the LSTM, but it learns how to regionalize based on the input variables that you use to drive it. And so that's really the secret sauce behind the AI approaches, is that they figured out how to regionalize in ways that I think are, leaps and bounds better than traditional hydrologists have, because we don't have the power or the tools in the past to essentially calibrate 500 Raven models at the same time and make sure we see all of the interrelationships in space between all the parameters. So I would say that's my high level description of what an LSTM does. But if you want to learn the mechanics behind an LSTM, well, now, you got to go to that reference that was posted.
Thank you. And I'm sure others might have resources that they can share in the chat as well. I'm going to just pause here again. If you would like to ask any questions live to the presenters, please just use the raised hand function on the control panel bottom of your screen, and we'll be able to allow you to unmute and ask the questions live. I have a question here for Dr. Craig from Hisham. Do you see that the delineations of the CLRH basin maker are more accurate and can override other tools? For example, OIT of the Ontario Ministry of the Environment. Are there efforts to have them adopted by the different regulatory agencies in different provinces and municipalities?
All right. So I believe, if I'm correct, and maybe Brian will tell me I'm wrong here, but I believe OIT is just a traditional terrain analysis.
No,
OIT is not.
no. OIT's
I'll let you answer this question then.
OIT is actually based on the Ontario Ministry of Natural Resources and Forests own burned-in FDR. So the province of Ontario has their own FDR that they burned in, much like what was done by our team here. But that was done many years ago. So OIT is essentially using the same flow direction raster that CLRH would use, except there are some slight differences, and we in fact have our own Ontario Lake and River routing product built for the province that matches the OIT delineations. So when you click delineate on OIT, it's doing the same method and using the same FDR that our Ontario Lake and River routing product actually uses. So that would be the answer there, I think. Hopefully that was clear.
And so in that case, the supplementary benefit of using something like CLRH would be the inclusion of lake catchment areas. That's probably a bit wiser.
Yeah.
Beyond that, we encourage you to compare yourself and see what you think.
Yeah, and OIT is only the watershed boundary. It's not the sub-watershed discretization. So
yeah.
Thank you to both speakers. I'm going to jump into our answered questions again. If Dr. Jalbert, if you can elaborate a bit more on this question, a great question from Simon Lin, asking if you could comment on other additional efforts that might be required to account for elevation differences within the same climate zone. Someone's wondering if this involves more data collection, testing other covariates, considering other distributions, etc.
Yeah, for that, it is considering different covariates. So we are trying currently to use the difference between the station elevation with the CAS-R grid cell elevation. So we try to do that. So if there is a large discrepancy between those two elevations, then we would have to correct it. This is our idea that we are testing right now. So for British Columbia, it's a bit more difficult than the other spatial domain in Canada. So we are still adjusting our model to that specific region.
Thank you. I can see, Brian, you're typing an answer right now. So question from Anonymous.
Yeah.
About Raven. I understand that Raven produces hourly outputs, but if subbasins stimulated by LSTM are there daily, is there a substantial smoothing effect?
So I would say that the reason that in the example I was showing that we were getting some decent variations in hourly stream flow is because when you simulate in a lake-based catchment with Raven, the lake is basically has a stage outflow relationship that it's simulating on an hourly basis, and so you can have variations at a sub-daily time step. So you get some distinct sub-daily behavior that you would have not necessarily expected by just feeding it with daily time step inputs from the LSTM. And the second thing I typed is that people have modeled stream flow with an hourly based LSTM, and that is possible, but you can imagine that that's very data hungry, and it starts to become a little bit more complicated to build an hourly LSTM model than a daily model. It's not impossible, and people have published on it. You can see neural hydrology for that kind of study. So yeah, we haven't utilized the hourly LSTM at the moment, but we could. But even if we did, then that still wouldn't give us spatially distributed predictions. Well, I shouldn't say that. Yeah, we just haven't used it.
Thank you. Okay, we have a couple minutes left on the clock. I do have one last question here. I'm not sure which speaker this is directed to, so I might just pose it to the panel from Jessica. I'm wondering if there are any comparisons as to how peak flows for input into hydraulic models change with improved hydrology models. Much of the peak flow generation also depends on land use, not only drainage systems. In your expertise, how would that come into play?
So I would say, the hydrology models do utilize land use information in addition to just the drainage system. So that is an additional input that's not in these data products that we're talking about. But that would be included in those models. So the question that as I see it, the question is fundamentally, do improved flow estimates from hydrologic models improve our hydraulic models? And I would say yes. The more accurate we can get those incoming boundary conditions, which are the drivers to the hydraulic models, they determine the hydraulic models output. If we can reduce the uncertainty in those, then we can reduce the uncertainty in those hydraulic model outputs because they're sequential, right? If you are using a model to generate the boundary condition to the hydraulic model, you want the best model possible. And so better models will lead to better downstream models.
Any last final remarks from the rest of the panel?
No, just thanks for all the great questions. It was fun to do this. I appreciate the opportunity. So thank you to the hosts and to the audience.
Thank you so much. And I, on behalf of CWRA and our team, our interpreters, and our partners at NHS, want to thank the speakers for their time. It takes a lot of time to prepare for a presentation like this, and for joining us for answering all our questions from the panel and from our audience. As a reminder, the recording of today's webinar will be available on our website. We hope you'll join us for future webinars. Any links in the chat. Please feel free to grab them now. We'll keep the webinar open for a couple of minutes. We've also popped up on your screen a short survey regarding today's webinar. Your feedback is valuable and will help us improve future sessions. Thank you so much for your time today, everyone, and I hope you have a great rest of your afternoon.
Thank you. It was well organized.
Yeah, very much so.
Thanks,
you.
everyone. Take care.
Yeah.
You nailed it. Good job,
Yeah.
sir.